We're very excited for today's webinar that will be presented by Julian Chambert on novel applications of anaerobic bioremediation for in-situ remediation of petroleum, hydrocarbons, and arsenic. A few housekeeping items up front. We'll be keeping all phone lines muted during the presentation to keep background noise down, and then we'll open it up at the end for Q&A. If you have any questions throughout the presentation or at the end, you can either raise your hand to ask them at the end or enter them into the chat box at any time, and we'll answer at the end. This webinar has been approved for 1 PDH credit. If you'd like to get a certificate for that, you can download the sign-in sheet that will be in the chat feature. We'll upload it in just a moment here, and there are a few questions in that you need to answer. Just multiple choice, so please take a look at that, and we'll post it again later in the presentation as well. If you have any issues downloading that form and you want credit, please send an email to daniela.savin@parsons.com and we'll get you that form. And then finally, this webinar is being recorded and we will have it uploaded to our YouTube channel in the coming days. So overall agenda is we'll introduce Julian as a guest speaker. He'll present a core value moment followed by his technical presentation, and then we'll have a Q&A session at the end. So Julian is a principal geologist at Parsons. He has over 15 years experience in environmental investigation and remediation with a focus on site characterization. He has earned a Bachelor's of Science in Geological Engineering and a Master's in Geology. And with that, I'll turn it over to Julian.
Thank you, Jessica. So for Parsons has like 6 core values, which you can see on the slide here, and I would like to focus on the last one, which is sustainability. To improve sustainability in our project, we use native plants as like a part of the site restoration following remediation programs. They can also be a lawn replacement in our gardens. The reason why those plants, the native plants, are a more sustainable alternative is that they reduce the need of watering and require minimal to no pesticide application, since they are more appropriate to the local climate where they are from. Also, they can help with managing rainforest rainwater runoff, and maintain healthy soil with deeper roots. If you decide to create a more sustainable garden, I found this website that could be a good starting point in your search. When you just enter your zip code, you can the website will suggest like native flowers and grasses that you can from your area that you can use. Just something to think about this spring when you'll be enjoying the weather outside. Before starting really to go into the presentation, I would like to acknowledge a couple of people. So our client, the Massachusetts Department of Environmental Protection, for their initiative to update the CSM, the conceptual site model, and explore alternative remedial technologies for the site. I would also like to thank the EPA Region 1 personnel that is working on this project. Within the Parsons team, a special thanks to a couple of team members who are making this project successful and interesting. First of all, Paul Feshbach-Marini, the Parsons project manager, Glenn Ulrich, our technical lead, Stefan Obey, who is our eyes and hands in the field, Jim Shaw, who built the pilot test system, Ted Schoenberg, who is working in the Parsons lab in Syracuse, New York, and finally, Melanie Beck and Jim Schutz, who are in charge of the groundwater modeling. During this presentation, I will introduce the site and some background information. Then we will show how Parsons was able to update the conceptual site model, tested different technologies during an in-house treatability study, and evaluate hydrogeological flow and chemistry under natural conditions at the site during a shutdown test. These different steps allow the Parsons team to design, build, and operate 3 pilot tests using 2 proven successful in-situ technologies. Finally, we will close this presentation with some takeaways messages and what the next steps will be at the site. Excuse me. The site layout and the conceptual site model. The site is the Barry-Maguire Superfund site, located in south of Boston, in Old Brook, Massachusetts. The Barry-Maguire facility operated as a chemical mixing and batching company between 1912 and 1983. As part of the cleanup process, approximately 248,000 tons of contaminated soil and sediment were burned on site between 1995 and 1997, and the resulting ashes were spread out on site above the groundwater table. A pump and treat system also has been operating for approximately 30 years at the site. The extraction wells are shown as blue dots on the aerial photograph, and the treatment system on the photo to the right. This system has been treating a persistent petroleum hydrocarbons plume comprised primarily of naphthalene and 2-methyl-naphthalene, and also including residual naphthalene. This plume is represented by the purple dashed line, and also an arsenic plume is present at the site and is shown in the red dashed line. Finally, the white dashed line on that photograph with the blue arrows show the location of a cross-section along the groundwater path. Here is our conceptual site model following the white cross-section line shown in the previous slide. It shows a buried glacial valley filled with mostly glacial outwash sand above till and bedrock. Fill and ash from previous remedial activities are above the sand. The CSM petroleum hydrocarbon plume in the purple dashed line and the arsenic plume in red are comprised within the yellow sand unit. The main receptor is the Colorado River, shown on the right side of the cross-section, and the groundwater is flowing from left to right on the figure. Within the petroleum hydrocarbon plume, BTEX compound weather out, but naphthalene and 2-methyl-naphthalene remain in the ground under anaerobic conditions. Most of the arsenic mass and flux is in the up-gradient sand, even though some of the maximum concentration of arsenic were found in silt. The primary current source of arsenic is the saturated sand. The 1986 ROD indicated that the groundwater will be cleaned up in 10 years with the pump and treat system, and obviously it didn't happen because we are still pumping almost 30 years later with no end in sight. In 2017, the Massachusetts Department of Environmental Protection, MassDEP, decided to evaluate alternative technologies because the current pump and treat system is not cost-effective for the long-term cleanup of the site. Therefore, Parsons was hired to evaluate a path to an in-situ alternative that will reduce the cleanup time and focus on the persistent petroleum hydrocarbons and arsenic plumes. Planning the process for the pilots. Changing technologies and ensuring that we are reaching the cleanup goal without endangering the surface water receptor have been planned in several steps. The first one was to update the over 30 years old CSM to have a better understanding of the site, which is shown in blue on the graph. At the same time, a treatability study was performed at our Parsons lab in Syracuse, New York, using soil and groundwater collected at the site to evaluate potential technology to use on site. After these two steps, 8-month pump and treat system shutdown was performed, where groundwater monitoring was performed regularly to understand how the plumes behave in absence of pumping conditions at the site. A groundwater model was created to evaluate the needs and define expectations during the pilot test design phase. In April 2021, the pilot test started and is still ongoing. Protection to the Colorado River is important to the project team. All along this process, we keep a close interaction with the regulator. For example, groundwater and surface water trigger values were established with the overlook of the EPA prior to the shutdown test, and they were re-evaluated prior to the start of this pilot test. Treatability testing. As the CSM was refined and updated, we had a better understanding of contaminant distribution and geochemistry, and factors controlling the distribution of contaminants at the site. So, using that information, the team developed ideas for potentially alternative remedial technology to treat the groundwater. Treatability studies in the Parsons lab were conducted to evaluate the effectiveness of various treatments to reduce contamination in groundwater. The treatment concept included 4 main processes, which are the enhanced arsenic solubility by injecting various treatment and chemicals and recovering the mobilized arsenic, enhanced in-situ hydrocarbon biodegradation and arsenic sequestration, ISCO, and ISCO with arsenic sequestration. The overall lesson learned from the treatability testing was that sulfate and nitrate treatments show positive results in capturing arsenic and reducing concentration of hydrocarbons. Also, we found that it will take time to see these results, especially for reducing the arsenic concentration. This slide illustrates the primary results from the enhanced hydrocarbon biodegradation and arsenic sequestration test. Naphthalene and 2-methylnaphthalene are the primary mobile petroleum hydrocarbon at the site. The graph on the upper part shows the concentration of naphthalene and 2-methylnaphthalene decreasing over time, only when the sulfate was added to stimulate anaerobic hydrocarbon biodegradation. As you can see with those yellow lines, that's where we added the sulfate. The picture on the bottom left shows 3 bottles. On the left, unanodized soil and groundwater. In the middle, black iron sulfide that formed after enhancing microbial sulfate reduction. And on the right, a nitrate-treated bottle with orange/green coloration indicating oxidation of ferrous iron. The graph on the bottom right shows arsenic concentration decreasing in the enhanced sulfate reduction and nitrate-treated bottles relative to the unamended controls in blue. The positive results using sulfate led to the novel concept of injecting sulfate for treating both petroleum and metal impacts at the site, including naphthalene, 2-methylnaphthalene, and arsenic, which are the primary contaminants at the site. With the finding of the treatability study, the team narrowed down 2 main technologies to implement in the field under 3 different pilots. On the left, the sulfate and enhanced sulfate reduction, or ESR pilots, are stimulating the anaerobic biodegradation of hydrocarbons in groundwater and soil, resulting in iron sulfide minerals generation to sequester arsenic from groundwater into less mobile forms. On the right, the nitrate pilot is using a denitrification technology to stimulate the anaerobic oxidation of abundant ferrous iron in groundwater and soil to generate a ferric iron mineral permeable reactive barrier for passive in-situ arsenic treatment, downgradient of the arsenic and hydrocarbon plumes. Shutdown test. The main purpose of the 8-month shutdown test was to evaluate how groundwater behave under natural conditions. On the map, the arsenic plume as mapped in the sand unit is shown in orange, and the residual hydrocarbon plume is shown in the purple contour. The red halos show locations where naphthalene increased during the shutdown test. The open black circles show no change in naphthalene concentration over time. Generally, an increase of naphthalene concentration was identified in the core of the plume. The graph shows the concentration trends of arsenic in purple, naphthalene in blue, and 2-methylnaphthalene in orange in 3 wells along the path of the plumes. The blue arrow shows when the pump and treat system was on. The graph on the lower left shows a typical response in the interior core part of the plume. Naphthalene, 2-methylnaphthalene, and arsenic concentration increased after an initial lag, and they subsequently decreased after the restart of the system. Naphthalene was found to be the contaminant that increased to the greatest extent during the shutdown test. Since no surface water trigger value concentration were exceeded, the shutdown test confirmed that the pump and treat system can be off for an extended period of time during the pilot test without any impact to the quality of the Colorado River or the groundwater under the river. The shutdown test groundwater sampling data consisting on one baseline, 5 events during the shutdown, and 1 post-shutdown event provided a good tool to interpret the pilot test result during which the system will be shut down as well. Pilot test areas and layout. This figure provides a view of the layout of the 3 pilot tests over the arsenic plume in orange and the residual hydrocarbon plume in purple. The 3 pilot tests are the sulfate pilot shown in yellow, the ESR pilot in red, and the nitrate pilot in green. The pilot testing is comprised of injecting 3 different treatments selected based on the updated CSM and treatability test results within the area containing hydrocarbons, which is also the primary contaminant migration area. All 3 technologies are designed to remediate arsenic, while the upgradient sulfate pilot is also designed to enhance hydrocarbon biodegradation. The first pilot test, the sulfate pilot in yellow, includes 4 injection wells installed in the upper part of the plume and designed to influence a large central area of the plume. The second pilot test, the ESR pilot, is in red, includes 3 injection wells and is using the same sulfate technology as the sulfate pilot, with the addition of lactate to the injection mixture to speed up the sulfide minerals creation. This pilot test has the smallest footprint and was implemented using portable equipment. Finally, the third pilot in green, the nitrate pilot, includes 5 injection wells in the lower part of the plume using a denitrification technology described in the previous slides. The blue dot toward the Colorado River is a source of groundwater needed for the sulfate and nitrate pilots, which is pumped up to the LNAPL building where the mixing, metering, and distribution to the injection wells are performed. In addition, this pilot test supply well capture contaminated groundwater during the pilot testing. A couple of pictures for now about the sulfate and the nitrate pilot test, which were those two. On the left, you can see the water supply well and the above ground piping. So the water, it goes from that well up to the hill to the LNAPL building, where the mixing is done for the sulfate and the nitrate. On the picture on the right, you can show the inside of which shows the inside of the LNAPL building. In green, you can see to the right the sulfate storage tank. The white tank in the middle is a nitrate tank. And finally, to the left, you can see the different injection lines, and also there is some metering pumps in the mix. Now we're going to be focusing on the first pilot test, the sulfate pilot test. A conservative fluorescein tracer was initially injected with sulfate. On the left to the map with those black circle, that's where the injection was done. Dye traps were deployed in strategic location, so within monitoring wells. The traps were left inside those wells between 1 day and up to 2 weeks. The dye traps are shown on the picture to the right, consisting of activated carbon particles stored in the little nets. The traps were provided and analyzed by Ozark Underground Laboratory based in Missouri. The map at the top shows the distribution of fluorescein in green and sulfate in blue after 8 months. The green halos on the map shows that fluorescein was distributed throughout the plume with just 4 injection wells. Sulfate was distributed 490 feet down gradient. The 3 red circles correspond to 3 wells location on the central line of the flow path. In the upgradient location, the fluorescein was delivered relatively quickly compared to the downgradient location, showing a lag in the fluorescein arrival. The actual flow velocity measure based on the tracer breakthrough agree with the Darcy calculated velocity determined during the CSM update. Fluorescein distribution within a cross-section. So the fluorescein is in green again, and in blue you have the sulfate, and which indicates that we have an effective vertical delivery throughout the plume. A preferential migration of fluorescein and sulfate was observed deep in coarser sand and gravel. The red circle with the associated graph highlights a 3-well cluster. The first response was observed in the deep well in the gray on the graph. Then the fluorescent tracer started to show in the intermediate well shown in the orange line. And finally in the shallow well, the blue line. The focus on the next slide will be the sulfate delivery. The map on the left is a close-up of the sulfate injection area, consisting of those 4 injection wells on the upgradient part of the site. The targeted sulfate injection concentration is 500 milligram per liter, based on the goal of delivering sulfate through the plume. The graph on the right shows the sulfate concentration over time, 5 feet down gradient of an injection well, which was nearly 500 milligram per liter every time we took a sample, confirming our pilot design. Looking along the groundwater flow path, sulfate distribution show a good distribution throughout the pilot test area. The 4 red circles show monitoring wells location along the flow path and the corresponding graph of sulfate concentration over time. In the upgradient part, concentrations of sulfate were around 500 milligram per liter, as we show in the previous slide. And in the downgradient portion of the plume, we were able to deliver 40 to 50 milligram per liter of sulfate, which is right on target with the pilot test design. Also, as shown on the right graph, we have a good correlation between the modeled sulfate distribution and what we are seeing in the field. Shutdown test to pilot test. This graph shows the naphthalene concentration over time throughout the shutdown and pilot test in a monitoring well location located in the central part of the plumes. This slide shows the importance of conducting a shutdown test for the interpretation of the pilot test results. As a reminder, the blue area shows when the pump and treat system was on. The black dashed line shows shortly after the second shutdown of the pump and treat system, illustrate the start of the sulfate injection. The early results during the shutdown test show continually increasing concentration of naphthalene in orange, up to approximately 900 microgram per liter, throughout the approximate 8 months after shutting the extraction wells off. After we restarted the system, the concentration decreased significantly. During the sulfate pilot test, sulfate concentration increased and naphthalene increased also and peaked at 280 microgram per liter, and then show a decreased trend. The muted naphthalene response and the eventual decrease of the sulfate concentration observed during the pilot test is the result of sulfate utilization in the hydrocarbon biodegradation process, indicating the effectiveness of the technology to degrade naphthalene. Hydrocarbon degradation. Going back to our plume map and looking at 4 monitoring locations screened in the deeper sand unit along the groundwater flow path, the results show where significant sulfate was delivered. Hydrocarbon degradation was observed. For example, in the top right graph, naphthalene concentration increased to over 1,000 microgram per liter and then decreased below 200 microgram per liter after the sulfate arrival. Focusing on the sulfate trend over time, on the top figure, an early trend shows sulfate concentration increased throughout the pilot test and are shown in the area in green. Notice that the sulfate concentration did not significantly increase toward the Colorado River. On the lower figure, later in the pilot test, the sulfate trend is still increasing on the upper portion of the plume and decreasing in most of the plume shown in red. Slide is looking at the naphthalene trend. On the top figure, early in the pilot test, naphthalene concentrations were primarily increasing, shown in red, which is consistent with the shutdown test. On the bottom figure, the later trend shows an overall decrease of the naphthalene throughout the plume in green. In an area with high naphthalene concentrations and an area near the Colorado River, naphthalene concentration were observed to be stable or increasing. Now looking at both the sulfate and naphthalene trends we just talked about, green indicates good results, and I'm going to tell you why. Where the sulfate was delivered in green on the top map, naphthalene concentration were decreased green on the bottom map. Near the river, naphthalene concentration are steady or increasing since sulfate has not been delivered there yet. Sign of arsenic sequestration. Graph on the slide show the concentration of naphthalene, sulfate, and arsenic for mid-plume shallow well. This monitoring location show a clear decreasing trend in arsenic concentration concomitant with a decrease in naphthalene and sulfate, which is consistent with enhanced sulfate reduction after a lag period. Because it takes time for bacteria to respond to injected sulfate, a lag period after delivering sulfate prior to the onset of stimulating sulfate reduction and the biodegradation of petroleum hydrocarbons was anticipated. Similarly, time is required to accumulate arsenic scavenging iron sulfide minerals after sulfate reduction is initiated. Sulfate concentration were initially low, but began to increase if you look at the third gray data point, as sulfate migrated to the mid-plume location, but decreased again to near baseline level at the last gray data point, indicating a higher rate of sulfate consumption. Arsenic concentration began to decrease after delivery of sulfate, which is an early sign that sulfate is being reduced to sulfide to generate iron sulfide minerals. Now, we're going to be moving on to the second pilot test, the ESR. And is shown on the left, the area where we have like those 3 injection wells and also 5 monitoring locations. The ESR pilot was implemented by injecting easily biodegradable lactate in combination with the ferrous sulfate. The purpose was to evaluate a rapid initiation of elevated sulfate reduction rates and iron sulfide precipitation for arsenic sequestration. A one-time injection was performed in April 2021, but the 4-day injection did not stimulate sulfate reduction or decrease arsenic concentration due to the rapid migration of injected substrate, and the sulfate was out of the pilot area. An optimized pulse injection schedule was implemented in August 2021, consisting in multiple frequent injection events extending over an approximate 3-month period. This optimized injection successfully stimulated sulfate reduction and iron sulfate formation, which sequester arsenic, as we are going to see on the next slide. This chart shows arsenic concentration reduction at 5 ESR pilot monitoring wells and 1 injection well. The green area showed the initial injection, and the red area showed the optimized ESR injection discussed on the previous slide. The purple line represents arsenic concentration that did not decrease in the well 35 feet down gradient of the ESR injection line. For the other wells, arsenic concentration observed at the end of the optimized injection decreased between approximately 1/2 to 1/5 of the concentration measured during the baseline event in May 2021. The lowest concentration was detected at an injection well shown as a single point on the graph in December 2021. Arsenic concentration remained lower than baseline concentration in all the wells 2 months after the end of the optimized injection program. Additional monitoring is needed to evaluate the longer term trend. Also, additional injection as part of an extended pilot test is planned in the coming month, and we're hoping to drive the arsenic concentration even lower than where we are right now. The picture on the right shows iron sulfide, the black solids found in the groundwater, in the perch water, sorry, from a monitoring well indicating iron sulfide generation. Now, the last pilot, the nitrate pilot test. As a reminder, in this pilot test, the nitrate was injected to stimulate the anaerobic oxidation of iron to create ferric iron minerals that are known to be effective at sequestrating arsenic. There is potential for the arsenic becomes associated with less labile forms of ferric iron, including magnetite, as it is reported in the literature. On the left of the figure, 5 injection wells were installed corresponding to the green triangle circled in black. The original injection design called for a continuous nitrate injection. After approximately 3 months, field monitoring results show that nitrate was consumed much quicker than shown in the treatability study. The photo to the right shows ferric iron minerals in groundwater recovered from one of the nitrate injection wells. The rapid precipitation of ferric minerals resulted in a buildup in injection pressure. So for those 2 reasons, a subsequent series of optimized pulse-like injections at higher nitrate concentrations was implemented, and nitrate was successfully delivered up to 40 feet down gradient. This graph shows the injection schedule and arsenic concentration at 2 shallow and 2 deep monitoring wells for the nitrate pilot test. Arsenic concentration did not decrease in the deep pilot deep monitoring wells, the orange and yellow line, where the nitrate was not delivered. Arsenic concentration reduction at the shallow wells, blue and gray line, were observed. Reduction were observed when nitrate was delivered during the optimized pulse injection. Arsenic concentration decreased significantly and remained low, approximately like 10 times lower than the baseline concentration for one of the well during the pulse injection. However, an arsenic rebound was observed shortly after the end of the optimized injection. A potential explanation is that ferric iron minerals that were formed and initially sequestered the arsenic later released the arsenic, likely due to reductive iron dissolution after the injections. For this pilot test, additional monitoring is planned to evaluate if arsenic becomes associated with less labile forms or ferric iron, including magnetite, that could happen over time. Finally, a couple of takeaways. The successful implementation of this pilot test program shows the importance of several previous steps. The CSM update, which gave us a better understanding of the site, the treatability study, which allow us to pick 2 successful remedial technologies, and the shutdown test, which permitted to properly interpret the pilot test results later on. looking at the sulfate and ESR pilots, and within only 4 injection wells, sulfate was effectively delivered 490 feet down gradient, preferentially deep, with a delay in the intermediate and shallow sand. Results indicate significant stimulation of naphthalene and 2-methylnaphthalene biodegradation in the early stages of arsenic sequestration. Sulfate is definitely a promising technology to stimulate both hydrocarbon degradation and arsenic sequestration. For the nitrate pilot, a series of pulse-like nitrate injection at higher concentration successfully delivered nitrate up to 40 feet down gradient. Significant reduction of dissolved arsenic and iron concentration extended to the shallow wells up to 12 feet down gradient of the injection wells. Unfortunately, recent results show rebound of arsenic concentration at these shallow wells. Nitrate can sequester arsenic. That was one of the findings, but the release of arsenic of ferrous iron minerals to the groundwater, the rebound, is a concern for this technology. Finally, to summarize my presentation, we are really encouraged by the result of the sulfate and the ESR pilot. They are bringing a new approach using sulfate injection to treat both remaining hydrocarbons and arsenic contamination in groundwater. These pilot tests are being extended for another 6 months, where the pump and treat system will remain down, to further evaluate the application of the sulfate injection technology to potentially replace the pump and treat system. The goal is to find an in-situ alternative technology that will be more cost-effective and lower the nearly $1 million annual cost of operation of the pump and treat system. In addition, in-situ technology will likely increase sustainability and climate change resilience by decreasing operation cost at the site and lowering waste generation, for example. And with this, I'm done with my presentation. Back to you, Jessica.
Thanks, Julian. That was a really interesting presentation on how petroleum hydrocarbons and arsenic can be treated in situ with some new approaches. So if anyone has any questions, you can enter them either in the chat function, we'll read them out, or you can raise your hand and we'll call on you. So I see you've already got a couple people. So I will be here. I will unmute you and then. Well, I don't know where Mahir went, so he just disappeared from the call. There he is. Okay, Mahir, you can unmute yourself now and ask your question, please.
Hey, sorry, Jess, once you said my name, I thought I have to lower my hand. But so, Julian, this is a great solution. Pump and treat systems, as in the 80s, were sold as the golden child. We know now that's not the case. And your results seem very promising. This is a great result, at least. My question is, as part of your pilot study, it seems like you reuse the groundwater from the site itself, which is a great sustainable way. But have you guys looked at the full life cycle carbon savings, or in terms of the sustainability of? One, you already know that the pilot study is not going to get you the end goal, but what is still the next 10 years if you keep running the pilot study? Have you guys modeled and said, this is how many tons of carbons can be saved, how many tons of waste that can be eliminated? I see $1 million per year cost, but there is a intangible cost of climate and resiliency that can be very easily added as a benefit to this pilot that you guys have done. Have you guys looked into that?
So thank you for the question. We haven't looked at it yet. I think we are still in the pilot test stage, which is really like, okay, we found like we did the treatability study where we're like, okay, in the lab it works. Now we are testing it in the field. And the next step will be like, okay, will that make sense to go full scale and implement like really like that technology for the site? And that definitely those questions can be raised at that point. I think when we're sure that we're like, okay, we're going to implement it, and what are the benefits of doing it.
Excellent. Great. Thank you.
You're welcome.
There's a question in the chat from Lucy Wu. How about arsenic in the soil? I'm assuming addressing arsenic in the soil.
So the sequestration will be like, we're going to keep the arsenic in the ground, and so that will not really reduce the concentration the concentration of the arsenic in the soil. Maybe I can ask Glenn Ulrich to chime in a little bit on that question.
Sure, I will do that quickly. Doing a great
you.
presentation and a really good, important question. Related to the question, one of the things that we've observed is there is a background concentration of sulfate, roughly 30 milligrams per liter, in groundwater that is naturally feeding the plume. And because of the low concentration, it doesn't result in a very expansive effect. But nonetheless, what we see in that upgradient portion of the plume where sulfate is naturally feeding is very low concentrations of arsenic in groundwater. And we collected soil samples from the saturated sands in that area, showing very high concentrations of arsenic, as well as iron sulfides, and very low leachability. We developed bioleachability assays to evaluate the leachability of arsenic at the site. And bottom line is, it looks like from everything we've seen that over time, as sulfate reduction progresses and we generate iron sulfides, that the arsenic becomes much less leachable in the soil. So that's giving us an indication that over the long term of injecting sulfate, as Julian described, that would be the goal, is to generate, to change the mineralogy to a more permanent, less mobile state. And of course, as you mentioned, Julian, the source of arsenic is the soil. So hopefully that helps with the question.
Yeah, thanks, Glenn, Julian. So we have Todd Bellinger. If you can go ahead and unmute yourself and ask your question.
Todd, I think you're still muted.
Well, we can come back to Todd in maybe another minute. Always technical glitches sometimes. So from Ron Krauschik, he asked, what factor was identified that caused higher nitrate reaction within the in-situ injections versus the lab studies? And if you want to read that question, it is in the chat if you want to see it written out.
Well, what is the, let's see, I need to read it, yes.
I'm sorry, second from the bottom. What factor was identified causing higher nitrate reactions within the in-situ injections versus the lab study?
That's a good question, definitely. I'm going to go back to Glenn again on that. He's our expert.
We don't, I guess the short answer is we don't know. However, we do have a university here at University of the Missouri School of Science and Technology. That's one of the questions that they're looking at. We provided them, or MAPP provided them samples. But the bottom line is we're not sure. Yeah, we don't know. Ron, good question.
Jessica, do you want me to read another question, or you're managing it?
I was just going to say, so Ryan Thomas asks, were the THC and metal analyses performed within the Parsons lab or at a commercial lab?
Commercial labs. definitely. Yeah, we were all the treatability study, like using the water, the groundwater, and the soil from the site to interact with the different treatment was done in Syracuse, and then we were sending samples of those analysis to get the arsenic concentration and the PHC and hydrocarbon. Yeah.
Okay, thanks. And then I think so. Todd Bellinger was having a technology issue, so I think we've got someone else that's going to read his question. Krista Diller, I see you have your hand raised.
Yes, that's Todd passed his question on to me since he couldn't get unmuted or enter it in the chat. He is curious about the mixing for the sulfate injections. He's like wondering how long each mixing event takes and what the frequency of the injections was to get to that 500 milligram per liter target injection.
So the mixing is done right now every other week. We have Stefan going to the site and mixing. So the process is like we are using a potassium sulfate powder, and we are mixing it with the water from the supply well into like a 150 gallon mixing tank. And then that batch is transferred to the sulfate storage tank, which is a 1500 gallon tank. So that's done every other week. It takes less than a day to do it. But like with the extension of the pilot, we saw like the sulfate utilization was increasing. So we would like to increase our concentration. And for that, we're going to increase the metering rate. And we're probably going to keep the same a mixing ratio of powder and water, and we're just going to do it more often. So probably we're going to go on a weekly schedule to do the mixing. Hopefully that answers your question, Todd.
So we've got another question from Laurel May. How much was sustainability a driver in investigating in-situ options?
Definitely, it's one of the driver. We generally thought about the fact that, yeah, it's much better than to use what we have on site, so that way we don't have too much things going on like in and out of the site. But we haven't, as I said before, like go deeper into that question since we are still in the pilot test stage of the project.
Okay, and then we have a question from Akshay Parenki. Have you thought about adding lactate or other sources of organic carbon in addition to sulfate to the upgradient injections to make iron sulfides more quickly?
We did, and it's yeah, that's why we tried it on the ESR pilot, because it's a smaller scale pilot. It's a very small footprint, and it's because that introducing those lactate into it will create will speed up the process. And instead of treating the entire plume, we will focus on the upgradient part and even maybe like the injection point. So the purpose of that sulfate injection is to treat the whole plume and not just like one area, like the upgradient area. We want to let the sulfate goes down with the groundwater, so that way you can create the sulfide minerals along the path, and then scavenge the arsenic along that groundwater flow path.
Okay, great. Thanks, Julian. And actually, I have a question. So with what's been going on in the world in the past months and weeks with supply chain issues, has there been any problems with getting the materials you need for your injection pilot studies, or do you anticipate having any issues as you go forward?
As we're doing it right now, we haven't had any issue. Distribution, yes, sometimes I'm just probably like most of the time trying to plan it a little bit ahead, or, you know, giving me a little bit more time to, okay, we need more sulfate instead of, oh, I'm going to get it in 3 weeks. I'm going to plan to have it in a month, things like that. We didn't have any shortage of treatment yet. That didn't happen for now, but that might.
Yeah, thanks. If there's any other questions, you can still raise your hand or put in the chat feature. But in the meantime, if we go to the next slide. The next webinar will be on June 8th, so that's a month from today at the same time. It's on the use of cutting-edge molecular microbial technologies to drive a successful, novel, enhanced bioremediation of legacy contaminants. So we hope you all will join us for that webinar. It'll be presented by Eleanor Jennings. And as I said, this webinar was recorded and we'll have it posted up in a few days. The form for PH credit has been posted several different times in the chat feature. And if you have any issues downloading that, if you want credit for today, you can just email either myself or Daniela.sabin@parsons.com. We thank you to everyone who joined us today, and great presentation, Julian. Thank you.